Hello everyone, this is the audio lecture for visually impaired students on the topic of electrochemical cells from Atkins physical chemistry. So, an electrochemical cell consists of two electrodes or metallic conductors in contact with an electrolyte, an ionic conductor, which may be a solution, a liquid, or a solid. An electrode and its electrolyte comprise an electrode compartment. The two electrodes may share the same compartment. The various kinds of electrode are summarized in table 6c.1. Any inert metal shown as part of this specification is present to act as a source of sink of electrons, but takes no other part in the reaction other than perhaps acting as a catalyst for it. If the electrolytes are different, the two compartments may be joined by a salt bridge, which is a tube containing a concentrated electrolyte solution. For instance, potassium chloride in agar jelly that completes the electrical circuit and enables the cell to function. A galvanic cell is an electrochemical cell that produces electricity as a result of the spontaneous reaction occurring inside it. An electrolytic cell is an electrochemical cell in which a non-spontaneous reaction is driven by an external source of current. Half reactions and electrodes. It will be familiar from introductory chemistry courses that oxidation is the removal of electrons from a species, reduction is the addition of electrons to a species, and a redox reaction is a reaction in which there is transfer of electrons from one species to another. The electron transfer may be accompanied by other events such as atom or ion transfer, but the net effect is electron transfer and hence a change in oxidation number of an element. The reducing agent or reductant is the electron donor. The oxidizing agent or oxidant is the electron acceptor. It should also be familiar that any redox reaction may be expressed as the difference of two reduction half reactions, which are conceptual reactions showing the gain of electrons. Even reactions that are not redox reaction may often be expressed as the difference of two reduction half reactions. The reduced and oxidized species in a half reaction form a redox couple. A couple is denoted oxidation/reduction and the corresponding reduction half reaction is written. It is often useful to express the composition of an electrode compartment in terms of the reaction quotient Q for the half reaction. This quotient is defined like the reaction quotient for the overall reaction. Q is equal to pi a j raised to the power mu j, but the electrons are ignored because they are stateless. The reduction and oxidation processes responsible for overall reaction in a cell are separated in space. Oxidation takes place at one electrode and reduction takes place at the other. As the reaction proceeds, the electrons released in the oxidation at one electrode travel through the external circuit and re-enter the cell through the other electrode. There they bring about reduction. The electrode at which oxidation occurs is called the anode. The electrode at which reduction occurs is called the cathode. In a galvanic cell, the cathode has a higher potential than the anode. The species undergoing reduction withdraws electrons from its electrode, the cathode, so leaving a relative positive charge on it, corresponding to a high potential. At the anode, oxidation results in the transfer of electrons to the electrode, so giving it a relative negative charge corresponding to a low potential. Varieties of cells. The simplest type of cell has a single electrolyte common to both electrodes. In some cases, it is necessary to immerse the electrodes in different electrolytes as in the Daniell cell, in which the redox couple at one electrode is Cu2 positive to Cu and at the other is Zn2 positive to Zn. In an electrolyte concentration cell, the electrode compartments are identical except for the concentration of the electrolytes. In an electrode concentration cell, the electrodes themselves are different concentrations either because they are gas electrodes operating at different pressures or because they are amalgam solutions in mercury or analogous materials with different concentrations. A. Liquid junction potentials. In a cell with two different electrolyte solutions in contact, as in the Daniell cell, there is an additional source of potential difference across the interface of two electrolytes. This contribution is called the liquid junction potential. Another example of a junction potential is that at the interface between different concentrations of hydrochloric acid. At the junction, the mobile H positive ions diffuse into more dilute solution. The bulkier Cl negative ions follow, but initially do so more slowly, which results in a potential difference at the junction. The potential then settles down to a value such that after that brief initial period, the ions diffuse at the same rates. Electrolyte concentration cells always have a liquid junction. Electrode concentration cells do not. The contribution of the liquid junction to the potential difference can be reduced to about 1 to 2 megavolt by joining the electrolyte compartments through a salt bridge. The reason for the success of the salt bridge is that provided the ions dissolved in the jelly have similar mobilities, then the liquid junction potentials at either end are largely independent of the concentration of the two dilute solution and so nearly cancel. B notation. The following notation is used for electrochemical cell. Single line, an interface between two components or phases. Dotted line, a liquid junction. Two parallel lines, an interface for which it is assumed that the junction potential has been eliminated. The cell potential. The current produced by a galvanic cell arises from the spontaneous chemical reaction taking place inside it. The cell reaction is the reaction in the cell written on the assumption that the right hand electrode is the cathode and hence the assumption that the spontaneous reaction is one in which reduction is taking place in the right hand compartment. If the right hand electrode is in fact the cathode, then the cell reaction is spontaneous as written. If the left hand electrode turns out to be cathode, then the reverse of the corresponding cell reaction is spontaneous. To write the cell reaction corresponding to a cell diagram, first write the right hand half reaction as a reduction. Then subtract from it the left hand reduction half reaction because by implication that electrode is the site of oxidation. If necessary, adjust the number of electrons in the two half reactions to be the same. Nernst equation. A cell in which the overall cell reaction has not reached chemical equilibrium can do electrical work as the reaction drives electrons through an external circuit. The work that a given transfer of electrons can accomplish depends on the potential difference between the two electrodes. When the potential difference is large, a given number of electrons traveling between the electrodes can do a lot of electrical work. When the potential difference is small, the same number of electrons can do only a little work. A cell in which the overall reaction is at equilibrium can do no work, and then the potential difference is zero. According to the discussion in topic 3D, the maximum non-expansion work a system can do at constant temperature and pressure is given by equation 3D.8. In electrochemistry, the additional non-expansive work is identified with electrical work WE. The system is the cell and delta G is the Gibbs energy of the cell reaction. Because maximum work is produced when a change occurs reversibly. follows that to draw thermodynamic conclusions from measurements of the work that a cell can do, it is necessary to ensure that the cell is operating reversibly. Moreover, it is established in topic 6a that the reaction Gibbs energy is actually a property relating through the term RT ln to a specified composition of the reaction mixture. Therefore, the cell must be operating reversibly at a specific constant composition. Both these conditions are achieved by measuring the potential difference generated by the cell when it is balanced by an exactly opposing source of potential difference so that the cell reaction occurs reversibly. The composition is constant and no current flows. In effect, the cell reaction is poised for change but not actually changing. The resulting potential difference is called the cell potential, E cell of the cell. The cell potential was formerly and is still widely called the electromotive force EMF of the cell. IUPAC still prefers to the term cell potential because a potential difference is not a force. As the introduction has indicated, there is a close relation between the cell potential and the reaction Gibbs energy. It can be established by considering the electrical work that a cell can do. Establishing the relation between the cell potential and the reaction Gibbs energy. Consider the change in G when the cell reaction advances by an infinitesimal amount at some composition. From topic 6a, specifically the equation delta Rg is equal to del G by del epsilon. It follows that at constant temperature, the maximum non-expansion electrical work We that the reaction can do as it advances by d epsilon at constant temperature and pressure is therefore dWe is equal to delta d epsilon. This work is infinitesimally and the composition of the system is virtually constant when it occurs. Suppose that the reaction advances by d, then Vd electrons must travel from the anode to the cathode, where nu is the stoichiometric coefficient of the electrons in the half reactions into which the cell reaction can be divided. The total charge transported between the electrodes when this change occurs is nu E NADE, because hence the total charge transported is minus nu FDE, because ENA is equal to F Faraday's constant. The work done when an infinitesimal charge travels from the anode to the cathode is equal to the product of the charge and the potential difference E cell. And this relation is equated to the one above. The advancement cancels and the resulting expression is nu Fe cell is equal to delta Gr. This equation is the key connection between electrical measurements on the one hand and thermodynamic properties on the other. It is the basis of all that follows. It follows from equation 6c2 that by knowing the reaction Gibbs energy at a specified composition, the cell potential is known at that composition. Note that a negative reaction Gibbs energy signifying a spontaneous cell reaction corresponds to a positive cell potential, one in which a voltmeter connected to the cell shows that the right hand electrode is in the specification of cell, not necessarily how the cell is arranged on the bench, is the positive electrode. Another way of looking at the content of equation 6c2 is that it shows that the driving power of a cell, that is its potential difference, is proportional to the slope of the Gibbs energy with respect to the extent of reaction. The significance of delta Gr. It is plausible that a reaction that is far from equilibrium when the slope is steep has a strong tendency to drive electrons through an external circuit. When the slope is close to zero, when the cell reaction is close to equilibrium, the cell potential is small. The reaction Gibbs energy is related to the composition of the reaction mixture by equation Delta GR is equal to delta GR naught plus RT ln Q. It follows on division of both sides by minus nu F and recognizing that delta GR divided by minus nu F is equal to E cell. That E cell is equal to minus delta G naught R by nu F minus RT by nu F ln Q. The first term on the right is written E naught cell is equal to minus delta G R naught divided by nu F and called the standard cell potential. That is, the standard cell potential is the standard reaction gives energy expressed as a potential difference in volts. It follows that E cell is equal to E naught cell minus RT by nu F ln Q. This equation for the cell potential in terms of the composition is called the Nernst equation. The dependence that it predicts is summarized in figure 6c.5 through equation 6c.4. The standard cell potential can be interpreted as the cell potential when all the reactant products in the cell reaction are in their standard states. For them, all activities are 1. So Q is equal to 1 and ln Q is equal to 0. However, the fact that the standard cell potential is merely a disguised form of the standard reaction gives energy should always be kept in mind and underlines all its applications. An important feature of a standard cell potential is that it is unchanged if the chemical equation for the cell reaction is multiplied by a numerical factor. A numerical factor increases the value of the standard Gibbs energy for the reaction. However, it also increases the number of electrons transferred by the same factor, and by equation 6c.3 the value of E naught cell remains unchanged. A practical consequence is that a cell potential is independent of the physical size of the cell. In other words, the cell potential is an intensive property. Cells at equilibrium. A special case of the Nernst equation has great importance in electrochemistry and provides a link to the discussion of equilibrium in topic 6a. Suppose the reaction has reached equilibrium, then Q is equal to K, where K is the equilibrium constant of the cell reaction. However, a chemical reaction at the equilibrium cannot do work and hence it generates zero potential difference between the electrodes of a galvanic cell. Therefore, setting E cell is equal to 0 and Q is equal to K in the Nernst equation gives E naught cell is equal to RT divided by nu F ln K. This very important equation, which could also have been obtained more directly by substituting equation 6a.15 delta G naught is equal to minus RT ln K into equation 6c.3 can be used to predict equilibrium constant from measured cell potentials. The determination of thermodynamic functions. The standard potential of a cell is related to the standard reaction Gibbs energy through equation 6c.3. Therefore, this important thermodynamic quantity can be obtained by measuring E naught cell. Its value can then be used to calculate the Gibbs energy of formation of ions by using the convention explained in topic 3d, that delta Gf naught is equal to 0. The temperature coefficient of the standard cell potential dE naught cell by dt gives the standard entropy of the cell reaction. This conclusion follows from the thermodynamic relation del G by del T constant P is equal to minus S derived in topic 3e and equation 6c.3, which combine to give dE naught cell is divided by dt is equal to delta SR naught divided by nu F. The derivative is complete, not partial, because E naught cell like delta GR naught is independent of the pressure. This is an electrochemical technique for obtaining standard reaction entropies and through them the entropies of ions in solution. Finally, the combination of the results obtained so far leads to an expression for the standard reaction enthalpy, which is delta HR naught is equal to delta GR naught plus T delta SR naught is equal to minus nu F into E naught cell minus T dE naught cell divided by dt. This expression provides a non-calorimetric method for measuring delta HR naught and Through the convention delta HF naught is equal to 0, the standard enthalpy of formation of ions in solution. The cell reaction is checklist of concepts. Cell reaction is expressed as the difference of two reduction half reaction. Each one defines a redox couple. Galvanic cells can have different electrodes or electrodes that differ in either the electrolyte or electrode concentration. A liquid junction potential arises at the junction of two electrolyte solutions. The cell potential is the potential difference measured under reversible conditions. The cell potential is positive if a voltmeter shows that the right hand electrode is the positive electrode. The Nernst equation relates the cell potential to the composition of the reaction mixture. The standard cell potential may be used to calculate the standard Gibbs energy of the cell reaction and hence its equilibrium constant. The temperature coefficient of the standard cell potential is used to measure the standard entropy and standard enthalpy of the cell reaction. Thank you.